Sorting is a fundamental operation in computing, powering everything from search algorithms to database operation. You've probably heard of insertion sort, selection sort, bubble sort, heap sort, quick sort, and many other sorting algorithms. But did you know that the built-in sort used by default in many programming languages is none of those you have heard about? The built-in sorting mechanism that runs under the hood in Java, in Python, in Rust, Android's Java runtime, and Swift is called Timsort, while C++, C Sharp, and Go uses a variant of a sort called introsort or introspective sort. Let's see how they work. Both Timsort and Introsort have a hybrid tag on them. They are designed to combine the strengths of multiple primary sorting algorithms to optimize performance for a wide range of data types and distributions. Timsort derived from merge sort and insertion sort. That design makes it adaptive while maintaining stability. Introsort, on the other hand, starts with quicksort but switches to heap sort when recursion depth exceeds a certain level. This gives it the speed of quicksort with the worst-case guarantee of heap sort. Timsort excels with real-world data, which often comes in partial order, while Introsort ensures consistent performance across all cases. Soon, we will benchmark all these sorting algorithms, and you will see how fast and effective these two are. But what if I told you we can actually sort 2 or 3 times even faster than this built-in sorts in certain scenarios? Stay tuned to find out how. Fun fact, did you know that the world record for manually sorting a deck of 52 cards was 36 seconds, which then was improved to 18 seconds in 2017? Now compare that with our sorting algorithms that can sort millions of items in less than a second. To benchmark various sorting algorithms, let's take an example from inventory management. Imagine a large supermarket chain with over 100,000 of unique items, each typically having a stock level of between 0 to a few hundreds of units. We need to sort this item by their stock level. Such sorting is a common operation in inventory management systems to identify low stock items, optimize replenishment orders, and allocate shelf space effectively. All right, so we will use an array of 1 million numbers, and we will report the average sort performance over hundreds of runs. Okay, so here is the benchmark result for 10 popular sorting algorithms. We will start by Timsort, which is the built-in sort option in Python, which gave us a very impressive performance of 158 milliseconds only. Selection sort, insertion sort, bubble sort were much, much slower that I could not even show in this graph. So 2,000 times slower. Next in line, we have shell sort, 50x slower than Timsort. Merge sort, 25 times slower. Radix sort, 12x slower. Bucket sort, things are getting better. Bucket sort, 11 times slower than Timsort. And then we have heap sort, only 9x slower. And then quick sort, 8 times slower. And introsort is much better than all other sorting algorithms we have seen here, but is still slower than Timsort. Now, here is the interesting part. There is one algorithm that can actually sort this data 2 to 3 times faster than Timsort. Let's discover more. That algorithm is called counting sort. So let's see how counting sort works first. In counting sort, we start by creating a count array of size max value plus 1. We initialize it to zeros, and then this array will store the frequency of each integer from 0 to max value. Let's actually consider an example to see how this is going to work step by step. Now, the next step for us is looping through the input array, and for each element, we will increment the corresponding index in the count array. This step counts how many times each number occurs in the input. So this is what we're going to have up until now. After that, we initialize an empty list called sorted array. Now we loop over every possible value from 0 to max value. For each value I, we append it to the sorted array the number of times it occurred, which we know from the count array. Now, finally, we will return the sorted array. As you can see here, we have two loops here. The first loop going to run n times, which is actually the length of the input array. And then the second for loop going to run k times, which is the range of the values in that array. So the time complexity of this counting sort is going to be theta of n plus k, which makes it very interesting for certain scenarios. Okay, now let's take a step back and look at the bigger picture. Most sorting algorithms we are familiar with, such as quicksort, merge sort, heap sort, and the rest, are comparison-based sorting algorithms. These algorithms make sense of the order by comparing elements to each other. This is a mathematical limit, not just a limitation of our current algorithm design. Counting sort, on the other hand, similar to radix and bucket sort, are integer sorting algorithms that take advantage of some characteristics in the input data and use that characteristics to sort that data much faster. A quick search online shows that there's so much confusion around the use of counting sort. There are questions like, why don't people use counting sort instead of quick sort or heap sort all the time? Why doesn't counting sort get so much attention that it deserves? Well, the key is understanding that counting sort trades generality for speed in specific cases. Let's explore exactly when counting sort shines and when it doesn't. Turns out, counting sort shines when we have integer or discretely ordered data and a limited range of values, where k is not significantly larger than the number of elements. One great example was the retail environment that we already considered, especially supermarket, department stores, or e-commerce platform. The number of unique items easily exceeds 100,000 of items, but each individual item's stock level would typically range in a reasonable range of few hundreds. Now, if you consider a healthcare app, the heart rate measurements typically range between 40 to 200 BPM, while you might have millions of users in that application. Another example would be population age analysis. While the oldest person alive is only 116 years old, most ages falls between 0 and 100, which makes counting sort very useful for demographic studies and resource planning. So in each of these three examples, the range of values are very, very limited. That makes our original time complexity of n plus k to be reduced to linear time complexity for sorting all data with such characteristics. But you gotta be very careful though. Counting sort isn't always faster. There are some cases where the range of values can be much larger than the number of elements in the array. One example would be the annual income of a sample population. Let's say we have a very small sample population of 100 people, but you gotta consider that anyone can be in your sample. For example, here, Elon ended up being in our sample population. Now, that will make our range to go anywhere from 0 to $56 billion, or another large number, depends on how good of a year Elon was having. Now, in this case, we are talking about billions for the range of the values. However, the sample size is very, very small. Annual income, regardless of having Elon in your sample population or not, often follows a log norm distribution with a very, very long tail. Counting sort would be highly inefficient here, requiring a massive count array and wasting a lot of memory. It can be as slow as an exponential time sorting algorithm. Always consider your data distribution and characteristics before choosing the sorting algorithms. I hope this video helped you understand when to break away from building sort and when to use counting sort for significant performance improvement. Please subscribe for more original content like this. Thank you for watching. I'll see you next time.